The title says hydrodynamic modeling approach, but it's more or less modeling approach. Well, I'll be talking more about hydrodynamics at first, but at the end I'll be kind of integrating how all the submodels or how all the features come together. So the basic outline of this will be understanding basic hydrodynamic principles. What are the key forces, what water bodies you're interested in, and what are the forces or what are the features that would be important in these kind of studies. So here we are now on the model development phase, because all of you have decided you will be using EFDC and EFDC Explorer. Maybe you went through different model selection criteria, but that's not the scope here. So we'll be talking about the model development and what are the things you need to consider when you are creating a model. So this is your typical sediment transport example. So here is water coming from ocean or long-term transport. Water is coming in and out, so there are erosion, deposition, right? There is a transport from rivers, and then load coming into your estuaries. So first thing what we need to do is create a conceptual model. So CSM, you'll hear it more when you're working with these type of projects, bigger projects. So they always say, like, get your CSM right first before doing anything. What are the things you want to consider? So if you're working with bigger projects with EPA or several parties involved, they always want to go back to your CSM and see if there is the fundamental flaw, or if you're not considering any factor or any processes in the system. So we need to define our spatial domain. When you're modeling coastal regions, the domain is infinite, but you need to constrain a domain where you want to constrain those. We'll talk about that more. Then you need to know at what time you want to run a model. Is it for 2 years, 3 years? Is it for 10 days? So those are the things you need to consider. And density is always an important factor in modeling. Be it a temperature or salinity, density will become an issue. So you need to consider those kind of things.
Could you please talk more about the density effects?
Yeah. So for example, if you have a thermal discharge, say you have a river, right? So what power plants do is take a cold water from the river or ocean, and then it uses for the power plant, and they discharge the hot water, right? So the discharging hot water has a higher temperature, but it has a lower density than the cold water. So I mean, density is automatically integrated in the model, but I just want you to understand that the effect you will be seeing is because of density.
Okay, so you're actually talking about the fluid density.
Yeah, fluid density. So if you are using, say, fresh water and salt water, fresh water will go over the salt water because salt water has higher density, and you'll see that salt weighs, so those kind of things. I just want you to be vigilant. Yeah.
Just to keep in mind that the water itself is not one single column.
Right. So in EFDC, it has equations where density, temperature, turbidity, they have a relation. So if you go into source code, and then the temperature dependence on density are explicitly stated there. So if you're using temperature, it will use the equation that considers only the temperature. But you have both salinity and temperature, it will lump both together, and then the density will be calculated. Yeah, choosing the appropriate spatial domain is very important. So you might want to choose where you have measured data available. So in coastal systems, if you don't have measured data, you might have to make a big regional model or something where you can extract the data that you can bound your models to. So it's really tricky where you end your boundary in coastal systems. In rivers, it's simple because you will have a gauge somewhere upstream, and downstream you might have water surface elevation, or you can go and take for surface elevations, but coastals are usually tricky. So the boundary locations should be chosen where the boundary values are either known or it can be measured. And in coastal systems, you can have harmonic constituents of a tide and then create a series from those constituents. So if you let's say you're working on Gulf of Mexico, then you will find out whether what harmonic constituents are important, whether it's M2, N2, O1, K1. These are different components. One is diurnal, one is semi-diurnal. M2, N2 are semi-diurnal. So you can do harmonic analysis of your time series and see what are the dominant harmonic constituents. Or you can always go to NOAA, and it gives all the harmonic constituents for your site. Most of the times, yeah. NOAA, NOAA, National. Okay, yeah. So the driving forces in any water body could be one of these. I might be missing something. If you can find out, let me know, I'll add it. So the things you need important is shoreline and bathymetry. You always need to cover as accurately as possible your shoreline. So I think if you have a really meandering and braided river, so the bottom friction and vegetation. So if you have a study area with a lot of vegetation, you want to consider vegetation because it has a resistance in the flow, and it would have impact on water quality because there will be respiration and photosynthesis. And inflows and outflows, this is the most critical part in any hydrodynamic modeling. So they say like garbage in, garbage out, right? So gravity and energy gradient is somehow related to the bathymetry. So if you have your bathymetry, you'll know which one is the higher elevation where the water should flow. So sometimes when you're assigning bathymetry, you wouldn't know it, but there might be some kind of island or some areas where there will be higher bottom elevation. They might not be accurate, so you might have to look at your slice and longitudinal profile and see how it looks. So if you think it should be slope, but if you see there is a bump somewhere in the bathymetry, then your water is not flowing in the right direction, then your model is screwed. So you have to check your bathymetry and take a look at profiles all the time. Just take extra time at the beginning of your modeling so that you don't have to come back later and realize, oh, I did this, and you have to run everything again. So it's important to get these things right at first. And tidal forcing, if you have a system where it has a tide, it's coming to the shore, then going back, then there will be a lot of impacts. Density, already mentioned it, and winds and atmospheric forcing has a lot of impact in your model. For example, if you're dealing with the lake will have a lot of impacts from the winds. So the direction wind is flowing, you'll see the water quality or salinity just shifted to that direction. So it's important to have solar radiation, temperature, wind, these all fall under atmospheric forcing. So it's important to have as accurate or measured data as possible. So if you don't have measured data, you can always compare between the adjacent stations. Usually the regional airports have weather data that you can use. In EFDC Explorer, let's say you have a water body and there are like 3 or 4 stations close to you and you don't know what to use, right? You can use all 4, and EFDC Explorer will take like chunks based on the distance between the model domain to those stations. So you can have a weighted, for this grid cells you can have 30% from this weather stations and 30% from another, and 30 or 40% from another, depending on how you assign. If you let EFDC assign, it will assign based on the distance from the model domain to those locations. And groundwater inflows, outflows, waves, and earth rotation. So earth rotation will have a very small impact if you are dealing with a smaller water body. let's say lake. But if you have a really huge oceans, then you might want to use a Coriolis. So what we need to provide is the latitude of your water body. Then it will calculate the Coriolis factor. Then it will go into the momentum equation, and that's how it's get included in your model. So these are the main forces, and some of the common water bodies we deal with are freshwater and rivers, lakes and reservoirs, tidal streams, rivers, estuaries, and coastal oceans. So this is an example of a simple one-directional river. So water is flowing from this direction to there. So some of the important factors that can be important here is the inflows, tributary inflows, and the main river inflows, direct runoff, and it can have an outfall, like some plant discharging their output, and it could also have a groundwater coming from somewhere that you want to include. So these kind of things are, these are the main things that you want to include. Bathymetry and shoreline is always important. Here you see it's a meandering, right? Now if you try to create a Cartesian grid, that means rectangular, you would end up having so many grids to fit this. But if you have a curvilinear that goes following the channel, then you will end up having less cells that will let you do more modeling, more repetition until you get your goal. This is a reservoir. So on reservoirs you have dams. So when you're representing the downstream, you would have the outflows from the dam, or if you have a weir, you can use a weir equation in EFDC for downstream, so that you'll have a better representation. I already stated that wind and wave are important. On lake and reservoirs, there will be direct runoffs. So sometimes we don't know what is the runoff from this particular stream. If you have money or time, you can do hydrologic modeling, create different subbations, and then calculate the flows from each subbasin and then tie it to the boundaries in EFDC. But usually we are on a time crunch, and we need to give them update and what's going on before we move to phase 2, right? So in those cases, it's helpful to find out the drainage areas of your let's say there is a small tributary. You can calculate the drainage area. Then you can go somewhere close to this area where there is a USGS station that will give you what is the drainage area, where you can pull out the time series of discharge, and then based on that drainage area, you can do a rough approximation of how much flow is coming into the system. Then another thing would be that this is a estuary. So the upper portion is similar to the lake where the river is coming. This is wider region, and there will be a lot of wind impacts here. But near the mouth of the estuary, there will be a lot of salt exchange and sediment exchange going on. So it's important to, where do you assign your boundary in these kind of cases? Are you going to do it right here at the mouth, or you are going to extend it somewhere like few miles towards the coast? So it's always important, what is your study area, where are you concerned? If you are concerned right at the mouth, you cannot have the boundary right at the mouth, because all of your results will be constrained or impacted by the boundary. So it's always a wise thing to go like few miles and probably make a circular kind of boundary at the coast, so that all the water can flow in and out without any problems. And I'll probably talk about what kind of boundary conditions you want to use on open boundaries. So open boundaries means water can flow coming in and out. There are radiation boundaries and there are fixed elevation open boundaries. Probably talk about those later. This is similar to the previous one. Here you can have waves, and then you can have breaking waves, you have surge. So it's important to have a wave component right in these kind of situations. So sometimes there will be high tides, so you might want to extend your bathymetric grids on these kind of regions, so you can represent whether those cells are wet during the high waves or not. The direct flows, there will be smaller tributaries. There can be groundwater recharge somewhere. So groundwater are usually represented on the bottom cell because it's coming from bottom, and then you can assign the flux, or you can assign the discharge or cubic meter per second. There is an option in EFDC Explorer that can help you decide which one you want to choose when you're representing the groundwater in your model. So in these kind of situations, the Coriolis might be important because it's a little bit bigger domain. These are simple things, I don't want to spend too much time. So when you're developing model, you can have empirical, analytical, and numerical. So empirical is based on the collection of data. You collect data, and based on those data you have regression, or you do some statistical analysis and create the empirical relation between different parameters, so you can have a good estimate. And analytical solution is you have an equation, you solve for it, and then you have a solution. But you cannot solve Navier-Stokes equation analytically. There are complex things that you cannot do analytically, but you can do it with using a numerical solution. So when you're doing a numerical modeling, it can be one-dimensional, two-dimensional, or three-dimensional. So it means like which direction you are concerned. If you have just a 1D river, if you have a river and it's well mixed in the vertical, and you are not concerned about what's happening on the right bank or left bank, so you can just have a 1D river with a vertical one layer. That would be a 1D model. But if you have a wide river and you are concerned about the width and the length, then you would want to have two direction, still have the one layer on the vertical, because it's well mixed. But if you are in a complex system and you want to see what's happening in each depth, then you will have to have different depths and different layers in the model. That's three-dimensional. So empirical, already talked about it. So in order to create a simple analytical model, already talked about it. All of us know about these kind of things. So the benefits of numerical model is we can allow complex geometries. It can be simple river to really complex estuaries with several islands and several forcings, and then it will allow for multidimensional, and we can always do hand casting and forecasting, because in any modeling you need to, in order to be sure your model is working, you need to compare your model with the data. If your model doesn't do a good job with data, it's no good. So these are the things that are important, already mentioned. So zero-dimensional is just like it's just like a box model. You say it's a water body, it's not changing with the space. You just have one-dimensional. A zero-dimensional, it's not mixing, it's not changing with any time. You can just plug an equation and then find out what's going on in that particular system. 1D, 2D, 3D already explained. So so the numerical approach is, first you create a grid for the model, then you assign what are the incoming flows, what surface elevations, then you run the hydrodynamic model. Before running sediment transport toxics, it's important to get the hydrodynamics right. You need to get the flows right in order to get the sediment loads right, because loads are flows time concentration. So it's wise thing to do first only the full hydrodynamics, then sediment transport, then toxics, then water quality. So the first thing, creating a grid, and the factors to consider, already these are repeating, but shoreline and bathymetry, and what are the driving forces and the physical processes. And grid development is an iterative process. You're not going to be done like create a grid and done. So you always come back to a grid and see if, oh, this area is not represented properly, I'm gonna extend a few cells here or make this portion deeper. So it's always iterative. So if you look at a model and there is nothing wrong with your model, you might want to check your bathymetry or shoreline if you're representing those areas, because you will have flows right, you would have everything right, but if your bathymetry is screwed, your model is going to be skewed with the bathymetry. So after you get the grid right, then the second thing you need to do is get the flow water surface elevation of the model right. So it's always a good thing to have only one layer in the vertical when you're doing the first round of iteration, because having multiple layers will just increase your computational time. The water surface elevation is not going to change a whole lot if you have one layer or 10 layers. So the multi-layers are important if you are going to introduce constituent transport, for example, salinity or temperature. But if you don't have the water surface elevation right, there is no point doing those kind of simulation first. So I mean, this thing I didn't do it very well while I was starting. I just created 10 layers and let the model run. It would take 20 hours to run, and then after 20 hours I realized, oh, I screwed up. Then if it's one layer, it will like take two hours to run your whole simulation. So just run with one layer, be sure, compare your water surface elevation at different regions, and then when you think your water surface elevations are good, then just introduce the number of layers you want to do. Applying initial condition, flow and boundary condition, and then you can calibrate your flows. Now you have done your first two parts right, then it's time to use full hydrodynamics in the model. Then you can introduce number of vertical layers, salinity and temperature, and then when you introduce those new parameters, then you need to also provide the boundary conditions for the temperature and salinity. So you have to have all the data together pulled up at first before you run anything. And surface heat exchange and thermal forcings, these are required when you are having a temperature simulation. Then you can calibrate to vertical velocity patterns and water quality, water column data. So after you have your hydrodynamics right, now if you want to do sediment transport, it's the right time to move to sediment transport. Then you define how many classes of sediment you want to use. If it's silts, if it's sand, or if it's clay. So you need to define how many classes you want to use, and based on that you define your boundary conditions and your grain size distribution on the domain. So we'll talk more about sediment transport, how it's done in day 3 and day 4. Then you need to build your initial and boundary conditions, and then calibrate your water column, TSS, total suspended solids, with your major data, and see if your model is doing a good job or not. And you can look at scour and deposition. So if you're expecting a deposition in some areas and you can see scour, it means somewhere your bathymetry is screwed, because it's creating an artificial pool and then water is just flowing to that particular region, and there is a lot of scour that's artificial. So in order to do a toxic transport, it's always important to do a sediment transport, because toxics use its sorption of the sediment. So it's all you need to have cohesive soil sediments at least in order to do the toxic transport. So toxic transport is built on the sediment transport. So sediment transport is calibrated first before doing any toxics, or you can do everything at once and run everything all again, but it's always add complexity as you move to different new feature. So that's the motto that we teach here. And you need to define the sorption approaches, your KDs, what you are going to use, and what are the loss terms. It can be volatilization or particle mixing. So you need to define those when you're running the model. And then at the last, you just do the calibration, and if it's reasonable, then you call it good. For water quality, you need to have a temperature parameter turned on, because all the water quality parameters are tied to temperature. So in EFDC Explorer, you will see if you have not activated the temperature, you will see the water quality is grayed out. So first you need to activate. It's just like giving the user kind of guidance of what you need to have to run the water quality. So you can decide if you want to have a sediment transport model or not. If you have sediment, you can use the sediment diagenesis submodel and define nutrient and DO series, build initial, and at last calibrate the model. Now that you know the basic approach, what we need to do, now we need to implement the model, right? So we are going to use EFDC model in the next session. EFDC model was developed. EFDC Plus is developed and maintained by DSI. However, EFDC was originally developed by John Hambrick, and then it was supported by EPA on several projects. EFDC Plus and EFDC Explorer modeling system provides a graphical user environment to build, analyze, and report results from EFDC models. So let's conclude this session here and take